we're going to talk about RMS, voltages and currents. And the reason we're going to create this RMS thing, we'll make some sense of that acronym as we go along. But the reason we're going to attack this problem is when we turn the handle on our generator, it makes alternating current. What that looks like is a sine curve. The voltage oscillates up and down between maximum and minimum voltages. And so the average voltage, because it spends half the time above zero and half the time below zero, the average voltage is zero. And the average current, we connect that up to a resistor, use that voltage to drive current. The current's going to do exactly the same thing. So the average current is zero. And so if we think about the power of our circuit, P equals VI, the average power is zero. But that's obviously wrong because we use AC all the time, like run lights in our houses, and the lights work, they glow, they turn electrical energy into light energy, into heat energy. And so we know that that's not right, so we need to find a sensible way of kind of thinking about AC voltages so that we can make comparisons with DC voltages. And so part of the problem we're faced with is that our AC voltage spends half the time above zero and half the time below zero. One really nice way of fixing that is just to square everything. So if we do square everything, what that does is it takes all of our negative values from our generator and it pops them up above the 0 volts squared line. And that gets everything into the positive territory, and that allows us now to calculate a sensible average of all of that. And so how do you calculate the average of a sine squared graph? That's like a really good problem to attack. And the way I thought we should do it is to think like, what's the area, what's the total area under our sine squared graph, like between 0 and 2 pi. I googled up what do you get if you integrate sine squared x, and turns out if you integrate sine squared x, with a little bit of working, you can persuade yourself that the total area under that graph between 0 and 2 pi is just equal to pi. That total area, that's just for a sine squared graph, not a V max squared sine squared graph, but that'll all come out in the wash. And so what's the average value of a sine squared graph over the first 2 pi? Between 0 and 2 pi, the area under those has to be pi. How high must that be? Half. Yeah, half. Cool. So all of this, what we've done with all of that maths is worked out that the average value of a sine squared graph is in fact exactly half the peak value. So the mean value of the squared graph is half of the peak value. That's not that, I mean, that's useful for finding an average of the Vmax squared, but we really want to have just V. And so to turn V squared into V, we really just want to square root it, eh? So what we want to do is take the root of the mean of the squared graph, the RMS, the root of the mean of the square. That's what we're doing. So if we take the square root of, so the average value of this graph is going to be half V squared, half Vmax squared, and so the voltage, the root mean square one, is going to be the square root of half V squared max. And the square root of a square is just going to cancel out. Square root of 1 is just 1. And so we just end up with V RMS is 1 over root 2 V max. You're going to find that one lurking on your formula sheet. And so what this does, the root mean squared value, gives us a voltage, a number that we can now use in our power calculations, and it's going to give us answers that are consistent with if we had DC voltages and did the same calculation. So whenever we're trying to look at AC and calculate power, we have to use the root mean squared voltage to do accurate power calculations. And in fact, look at an appliance that you buy in, like in New Zealand, it's going to say 240 volts, or maybe sometimes 230 volts. And that's the root mean squared voltage that we've got in New Zealand. What might the maximum voltage, like our power plugs, they don't sit at 230 volts. They go up higher than that, and down much lower than that. What's that maximum voltage? We can just rearrange that equation to be V max is root 2 V RMS. Let's go with the 240 volts. V max is root 2 times 240. We end up, I think it's about 440, isn't it? 339. Which of course has implications for how good our insulators have to be around our wires, because when we're designing our wires, we're not going to design them to have insulators thick enough to resist 240 volts, because we know that actually that voltage 50 times every second is going to make it up to 340 volts. So we're going to need to have our insulators just a wee bit thicker to cope with that higher voltage. Exactly the same maths goes for current. So I RMS is 1 over root 2 times I max. So what we're doing, we've got our graph that the average is 0, but we want to make a meaningful average. So we square it, find the average, which is just half the peak value, and then square root it. And it's that half hanging out in there that gives us the 1 over root 2, the factor of 1 over root 2. Just a lot of maths to prove that it's a half.